Hello, good morning, and welcome to this seminar from Lancaster University. It's the latest in a series on developments in materials science in conjunction with the European Regional Development Fund project GISMO. GISMO is Greater Innovation for Smarter Materials Optimisation, and I'm James Stancombe, Project Manager for GISMO. We're pleased to be joined this morning by Professor Pedro Rivera, the LPW and Royal Academy of Engineering Research Chair from the Materials Science Institute at Lancaster. He's going to speak on the use of new alloys in additive manufacturing and the business opportunities that they present.
So I wanted to introduce to you a case for the need to develop new alloys for additive manufacturing, and why this is a business opportunity. Why do we have any concern on additive manufacturing? Well, first I need to put things in context, and I need to say that my focus will be on metal additive manufacturing. So there is a lot of work around polymer-based additive manufacturing. However, this is, in terms of advanced technologies, metal additive manufacturing is usually thought to be related to products that are subjected to more demanding applications. So, I don't know, electric cars, turbine blades, and nuclear reactors, structural components for these. So, additive manufacturing is a fast-growing industry. So these are real data in billions of euros. So in 2019, the metal additive manufacturing was in the range of 2 billion, and this is forecast to increase to about 6 billion in 2024. I would say that as such, this makes additive manufacturing the most prominent, fastest growing industry nowadays as a manufacturing industry as such. So this is about 25% a year, which is quite significant. So there's a case for investing in additive manufacturing just because of the market growth. But what it is, just before I justify further statements on the technical side, this is how metal additive manufacturing looks like. So you have a laser beam, which is melting the material and is producing this layered material. This is more clearly seen in the next slide, where you see this complex shape and you see there's a rack that pushes powder, and by the powder bed move downwards, and slowly you 3D print a component which typically has a rather complex topology. So how does this work? Metal additive manufacturing can be divided into two branches, two types of metal additive manufacturing. You have powder bed techniques and powder bed techniques. Now, powder bed techniques could comprise laser powder bed fusion, electron beam melting, and powder bed techniques can include the fed ones, laser metal deposition. Now, people at the moment, the general thinking is that laser powder bed fusion is the most prominent technology that is going to emerge. Now, how does this work? You have a laser. The laser is focused onto the powder bed and is scanned through, and it leaves behind a trail, which is a solidified melt pool. Here you see that the laser can move towards the left and then towards the right. This zigzag kind of scan strategy is one of the many that is available. There's a number of parameters to which I'll refer in a moment, but the scan speed, you can see that is an important parameter, such as the hatch distance and the layer thickness. Rather than having a laser, electric beam could be used. This uses more energy and it produces larger melt puts typically. And in contrast with this, there's the powder fed techniques, where powders can be fed, and these powders are of different composition. This is very useful to functionally grade components that have different compositions. More in detail, and here I don't want to confuse you with a lot of technical details, but it's important, I guess, that you realize what can be controlled in laser powder diffusion, and why is this so different to conventional rod technologies. So we have a laser beam, and the laser can be focused, and the focus is onto a point. There's a laser beam size, which is melting this red highlighted cube. There's this V step indicates the speed of scanning, how it moves towards the right, and leaves this trail. Now, the parameters to consider are this hatch distance. So what is the distance between adjacent lines that are scanned? And the layer thickness, because when I move the powder bed downwards, there's a thickness to the layer. You can imagine how important this is for many reasons. If the hatch distance is massive, I don't melt the material properly because I leave spaces without melting. And the same can be said about the layer thickness. Now, why this hatch distance can be calculated, I will not elaborate how, but I'll call it uppercase delta, and the layer case thickness, lowercase delta. Now, why is this important? And this is the key thing that I want you to remember, that when I melt subsequent layers, then there is a temperature increase, and the temperature can go above the boiling temperature of the material, so I can lose material, or above the melting temperature of the material. So this is the case of 4 samples that we printed. And here you see how when we change printing parameters, we can have very different temperature signatures onto the powder bed. This is when each of these peaks represents one of the cycles of the different layers that are printed. And I don't want to discuss the detail, but I want you to realize first that by small changes, very small changes in the scan speed of, let's say, 750 millimeters per second to 200 millimeters per second, I can change these patterns that can go from boiling the material literally to just melting it a bit. And how, look at the horizontal axis. The horizontal axis is time. I can produce these layers in 80 milliseconds or reduce that time to 20 milliseconds. So that means that the time I need to print the material and to actually make it solid is in the range of tens of milliseconds. When I cast an alloy in industry, an ingot will take sometimes days to cool down. So you can imagine that if I can print with a laser within milliseconds, each of these layers, when cooling takes place, this results in a contraction that produces a massive strain in the material. This massive strain could be very negative because it can produce cracks. When you cool something very quickly, cracks can be produced. But at the same time, there is a chance that those strains induce strength in the material. And I'll refer to those features, the positive features. So once I learn how to control my material and not to crack it, then I can tailor its properties. And the first lesson to learn is most of the materials that are used at the moment industrially for 3D printing were designed for rod technologies, for hot working, rolling, and so on. So this is the first case for new alloys, for new materials for additive manufacturing, that if I design those new alloys, I can, for instance, avoid cracking. So I want to show you that sometimes when people present these new technologies, they are a bit too optimistic and they start to show unrealistic expectations of the material. I remember always how when carbon nanotubes were considered to be of industrial relevance, people speculated about space elevators, how you can construct a carbon nanotube that will go to the outer space, but no one proved it. But in this technology, people are already printing components. For example, this is the fuel nozzle for an aero engine, for a GE, General Electric aero engine. And the fuel nozzle, I read a few days ago that they have already printed 30,000 of these components that are flying. So 3D printing technology of metals is real. And why is it real? Because in the fuel nozzle, in the inside of it, I can achieve this very complex morphology. And you can imagine that in a technology such as forging, I need to deform the material from outside and shape it. And these sort of complicated shapes cannot be achieved with regular hot or cold working technologies, because there's no way to deform inside the material. Whereas when I'm building the material in layers, I can achieve these very, very complex shapes or topologies. Turbine blades is another very interesting example. I am not aware of turbine blades at the moment being printed, but I know very well that there is massive effort by a lot of large aero engine producers to replace existing single crystal turbine blades by these 3D printed counterparts. And here, the interesting bit is that you have these veins that allow the heat flux and the centrifugal forces to expel the heat, which allows me to increase the operational temperature of the aero engine, which in turn allows me to develop more efficient aero engines and save energy and decrease emissions. The key is topology. And when people talk about 3D printing, they always talk about topology. And this is very old. And I think that if people talk to you about the great shapes that you can achieve and how you can develop a new product based on topology, you're talking about 30 years old technology. This is really old stuff. The ability to achieve complex shapes is interesting, but it's just the start of what you can achieve with 3D printing. What is what you can achieve with 3D printing? You can achieve entirely new functionalities based on the characteristics of the alloys. And this is my second case for new alloys for additive manufacturing. This is a nice paper that was published a couple of years ago that shows how the turbine blade, when you see the cross section of a turbine blade, you realize that you can actually 3D print it, producing these so-called architected materials where I replicate grains in different directions that are tailored so that all the stresses are absorbed in different directions. So I can actually tailor within each of these components of the assembly. I can have different structures. This is a so-called FCC structure, which has a certain type of lattice and a different type of lattice here. So I can three-dimensionally build something that is different, but in order to build it and to make it work so that it absorbs efficiently the stresses at high temperatures, I need to develop new materials. How can I exploit and develop these new materials? Here's the second part of my talk. This is a concept that I introduced, which is that of the modular alloy design. So people talk about functional alloys, but you can actually, the functional alloys are usually based upon the fact that you have different powders. But as I discussed, the technology of fitting powders of different species is not the most attractive, because the ability to control the laser in the process is much lower than in the laser powder bed fusion. Here I have a powder bed where I shine on the laser. I focus it onto this scan line. And there's a hatch distance and a layer thickness. And what is remarkable is that just by controlling and changing slightly this hatch distance, layer thickness, but also the power of the laser and the scan speed, I can achieve very, very different properties. So I don't need to change the material. I can play with a single material and change its properties quite significantly. And this is what I call modular design. So I can, like Lego, I can have different bits and pieces that I assemble together. And by changing the parameters of the left-hand side, I can assemble something with different properties. And you are going to ask me what kind of assemblies you can achieve. Well, this is the most technical part of this presentation. And I want you to bear with me for about 2 minutes, because I really don't like when people present something and it is just theoretical. I can show you that we can actually construct all these different structures. There are 8 types of structures that I'm proposing, and they can be combined in a nearly infinite number of ways when you consider the possibility to develop a product in 3 dimensions and the different choice of new alloys that we can have. So first, I know that most of you are not metallurgists, but bear with me for a few minutes. Metallurgists talk about grains. So the ability to assemble grains in a structure, this goes from sizes of 10 microns to 10 nanometers. So 10 microns, to put it in context, is about 1/5 of the thickness of your hair. So when you see a metallic alloy, it's composed by grains. And about 10,000 times lower in scale is a nanometer scale. 1 nanometer is about 3 atoms in size. What I'm telling you is that by changing the laser printing or scanning parameters, I can change the structure in all these ranges from about a hair size to about a few atoms in size. What can I achieve? I'm not going to justify my statement of how, but there's plenty of literature that I can share with you to demonstrate that this is actually feasible. And I'll start with the grain structure, which is what I said that metallurgists usually play with. The grains are responsible, in the case of additive manufacturing, for texture. You can see texture means that you can orient them in certain directions. And with texture, you can control the strength, but also the stiffness. Stiffness is really important because a material that is very stiff will not deform. And if it's not rigid, then it will be elastic. This is important, for instance, if I want to 3D print bone replacements, which is an emerging technology. Martensite is one order of magnitude less in scale. Martensite is really strong. Martensite comprises a lot of the hardest engineering components that you have, for example, bearings or shafts. So martensite is produced by these layers. They are called laths that are stacked up and give you massive strength. But martensite is quite brittle. That's what I usually want to combine martensite with other structures that are ductile. Precipitation hardening. When I print a material and when I age it, I produce these tiny precipitates that are particles that are usually in the range of hundreds of nanometers. So that is about 1,000th of a hair size. And they imprint strength. And twins as well give me strength, but massive ductility. Twins are defects that appear in the material upon 3D printing them. The nanocellular structure is a form of grain, but is about 1,000 times smaller and gives me massive strength and excellent wear properties. If I want to print a material like a bearing or something that is subjected to friction, then these nanocellular structures are ideal to provide wear resistance. But always when you produce an alloy that is very strong there is a problem called hydrogen resistance. So we can tailor the formation of precipitates to prevent the embrittlement due to hydrogen. Last are these two very small ones, features, which is a passivation layer. The fact that when I print, I can promote the existence of an oxide layer that impedes oxidation, and last, the presence of a saturated solution. The fact that 3D printing, because it's so fast, allows me to saturate with solutes and alloy that otherwise will not happen, and this can give us significant strengthening as well. So I can produce all these 8 types of moduli, and I can control them by controlling the scanning parameters and by designing new alloys. And this is not just good wishes. There's plenty of techniques. For example, optical microscopy allows you to see what happens in terms of the development of cracks or pores. Scanning electron microscopy allows you to identify the orientation of the different grains. High resolution transmission electron microscopy allows you to see all these nanocellular structures, and the ability, you can actually, in the transmission electron microscope, identify small variations in concentration. So this can all be observed. It's not just a theoretical formulation. This is something that can actually be achieved. And this diagram is just to show you that across the scales, for example, this is the engineering scale. This is one of the examples that I'll be referring to, which is a bearing. This is a bearing ball. And I'm just saying that you can have a bearing ball which has a lattice structure at the center, which makes it very light, and you can print a hard surface. Then you can go down the scale. Here I'm going from a macroscopic engineering scale down to 1 atom, which is 10 to the minus 10 meters. And these are the characterization techniques. So as I mentioned, all these features and defects, the pores, the cracks, the fact that I print powders and their size, their grain orientation, the nanocells, there are techniques that cover across the scales all these features. They can all be observed. But matching each of these techniques, there is a modeling technique. So I can compute and prevent or control each of these features. For instance, the finite element analysis allows me to describe at the sub-micron scale or the micron scale. COMSOL is one such software. But I can use the so-called thermostatistical theory, or CALFAT, which is computational thermodynamics, to tailor the presence of grains, or finite element method to go down in a scale and understand how all this interacts at the macroscopic scale. And also the precipitation and the segregation. There's kinetic software, phase kinetics that I can use. So the bottom line here is that if I want to describe all these different modules, all these different microstructures that can be controlled by 3D printing, there is both a range of characterization techniques that allow me to describe them across the scales. And in addition to that, there is a range of modeling techniques that allow me to compute them. So we are at a unique crossroad in technology here, and I want you to realize this. We have an emerging technology that is lacking materials because all the materials were developed for raw technologies. That emerging technologies allow me, like Lego, to print modules at different locations in products. We have experimental techniques that allow me to observe those moduli that I can print. And we have modeling techniques that allow me to tailor to produce that assembly. So this is not just fiction, this is real. We have the techniques. It's just a matter of developing this further. Now, how can I develop this further? I want to, in the last part of this presentation, to introduce 5 examples of how I think this can be, these concepts can be put together. The first is that of armor. So armor is important for I wanted to produce this very vibrant example of a bullet that is disintegrated upon contact with an armor plaque. How does this armor material works? Well, so cracks, when the bullet comes, the crack in a non-armor material, regular material, a crack will cut through the material and it will penetrate it. But armor materials are usually composed of these layered structures where you can have a very hard material such as martensite, and I already show you that we can 3D print literally martensite. But if I change the scan speed and the laser power, I can produce a solid solution, which is soft. So when I layer these materials, the cracks cannot penetrate, and I can produce an armor material. This is very similar to the principles that nature uses in terms of seashells. Probably when you have been to the beach, you have seen that oysters and other forms of shells are incredibly tough. So if I try to press them, it's very hard to produce a crack, and that's because they produce these layers that grow on top of each other. That's exactly how nature works. The layered sea shells are so tough because, such as 3D printing, they produce these layers of different properties that make crack propagation so difficult. So that's my first concept, the ability to produce armor materials for which we can layer very hard but also very soft alloys or layers that impede the propagation of cracks. The second example, as I already outlined, is that of bearing elements. Bearings are really, really interesting components because, as you can see here by the rollers, the color represents the stress to which the rollers are subjected. So red represents very high stress and blue represents low stress. So of course, the points in contact are the ones that experience a lot of stress. But what is interesting is that you can see that at the center of the roller, there is very little stress. However, all the bearings that are produced nowadays, all of them are solid. All the rollers are solid and the bearing rings are all solid. And you can think to yourselves, what a waste of material this is, because I have properties at the center that I don't need. Essentially, I could save material if I would make the center of a different nature. So what I'm proposing is that you create a more hollow core part of the roller that is this lattice type of structure, whereas the contact surface is a nanostructure material. Why nanostructure? Because the nanostructured metal gives me ultra hardness and it displays great wear properties, or is, it's resistant against wear. I can also produce this solid solution at the outer and inner bearing rings. So what I'm trying to tell you is that I can produce nowadays bearings that will save weight. What application can I give to this? For instance, aero engine. The aerospace bearings are one of the most expensive components together with the shaft in the aero engine. So if I can reduce the weight of them, I can make, again, those engines more efficient because there's less weight that they have to carry with them. Third example is that of medical implants. So this simulation shows you what happens with the, with the human body, with the limbs, and in this case, with hip replacement. So nowadays, medical implants are forged, usually. So you can see that the medical implant, the hip replacement, has to have very interesting properties. And I am saying that the potential quality of the medical devices or the hip replacements that are 3D printed can seriously exceed the properties of the rod technologies. Why is this? Just look at the properties that I need, or the performance that is required for a hip implant. First, it has to endure this friction. So it is rubbing onto the hip, which could be another hip replacement implant. It's rubbing constantly. And that is where the material will fail. So that's one thing that you need. The second is that the body of the hip implant would be inserted into the femur. This has other properties that are of great interest. The human body has different stiffnesses, and that's where I show you the granular material early. I told you that we can print in different directions, and that changes the stiffness. And that is the reason why these hip replacements could be superior in when they are 3D printed, because the grain structure, I can print it in different directions, and as such, I can change the stiffness, and I can mimic what happens in bone. So I can produce more appropriate medical implants that replicate the load, the complex loading in human body, and that can be readily inserted. In addition to this, I can print the surface, the cap here, that is producing this constant friction in a nanostructural fashion so that it doesn't wear. And I can also produce a L, which is the layer, the passivating layer, because the human body contains blood and oxygen and very complicated fluids there that I wouldn't like to see myself, but they're out there. So they oxidize the femoral or the hip replacements. So the layer, the passivating layer is essential. So I'm proving here that I have the potential to 3D print in layers a hip replacement that has this mixture of moduli, the granular material that gives me tailored texture, the passivating layer that gives me resistance to corrosion of the fluids within our body, the nanostructure cap that gives me the massive wear resistance. Fourth example I wanted to show is that of turbine blades. So this is animation of how a turbine works. You see the blue represents cold air, which is then mixed by the fuel nozzle that I introduced earlier, and it's 3D printed and it's flying now. But turbine blades, which are the elements that transform the kinetic energy of the burnt fuel into a rotating rotating energy that produces the thrust that makes the turbine move forwards. These blade materials require very special properties. If 3D printed, they have these topological benefits, but they also need to be high temperature resistant, and they need to have some form of flexibility. And recently, there's a new branch or new group of alloys that has been discovered in the last 15 years called high entropy alloys. And these high entropy alloys can be changed significantly just by changing their composition, and I can achieve different types of structures in them. For example, the solid solution, the twin structure, or martensitic structure that can give me different, as I said, textures in the material, twinning so that they can deform properly, or I can make them very rigid at different regions within the same turbine blade. So in addition to have the topological benefits, the complexity of the shape of the turbine, 3D printed ones because of the veins that I mentioned earlier, I can also change the strength at different locations and, make it high temperature resistant. The last option that I wanted to talk about is that of die elements. I'm conscious, and I can see that many of you are already anticipated that 3D printing is a slow process. So But there are technologies, for example, stamping technologies that produces these complicated shapes, where the shapes are actually the result of an M-bill like this one that is hitting on the material, in this case sheet, to produce this profile shown here. Now these M-bills are unique. So 3D printing could be ideal for high technology, expensive, topologically rich components, but also for these components that require a certain complicated, unique shape like M-bills. These M-bills can stamp maybe millions of pieces, but I need just one M-bill for a certain shape. So if I can 3D print the M-bill, and the M-bill, as you can see, requires very, very interesting properties. When you punch the M-bill and produce this shape, there's a lot of friction, so you need to have wear properties. So M-bills can have this nanostructure material at the surface, which I said is very much wear resistant. But I can have tough core that has a certain grain orientation, or a martensitic one that is very, very strong. So this is my last example of how I can produce these modular 3D printed elements that require the use of new alloys and that also allow me to functionalize the material, but without changing the composition, but just by changing with existing technology the parameters. I just need to develop new alloys. So there's challenges, there's no fairy tale, there's always compromises. The 3D printing of alloys can produce this horrendous, the scale marker here is not clear, but it's about 0.5 millimeter. I can produce these horrendous pores, but if I change the 3D printing parameter, I can avoid those pores. So one way to foster this technology is to develop new materials that are resistant to pore formation. Also, there are other challenges. For example, recyclability of the powder. How can I reuse the powder to save material and to be environmentally friendly? How can I minimize the energy that is used in all these production of powders? Also, the end of life of product. And here's where I think 3D printing technology can be really interesting because, for example, the dies, I can produce swarf later on when they end life, and I can remelt them, and I can transform it into a circular type of economy. So there are great opportunities in materials for 3D printing and in the development of these recyclable, potentially new materials. So James, who has the commercial eye that I lack, indicated me how can you implement this additive manufacturing in your own products. I'm conscious that you come from a range of different industries. Some of you seem to come from oil industry. Some of you are in dye industry, from additive manufacturing. Well, I think the equation is balanced when you factor in how many products are you going to fabricate. If you try to 3D print 1 billion identical products, maybe it's not the best technology, but if you're talking about tens of thousands or thousands, it is a very interesting option, especially if the value of the product is very high. It's not the same to 3D print, I don't know, very cheap product than a turbine blade, which is very, very expensive. And especially if you want to increase the properties, then 3D printing can definitely be of interest. 3D printed products are stronger, they are more resistant to fatigue, they can have better or equal properties to in terms of irradiation resistance. That is better, definitely. And as I looking into the future, they are more sustainable because you can recycle them and manufacture independence. And this is one thing that we learned from COVID-19, that if you have a production chain where you have the supplier of your material in China, the assembly in Mexico, and then the sale in the UK, then you are not manufacturing independent in terms of your manufacturing chain. So the additive manufacturing production chain is very compact. Just produce a powder and print it and post-treat it. Very simple. So you can be independent in terms of your manufacturing capabilities. And to summarize, so metal additive manufacturing gives you the possibility to produce new products of different kind, displaying great properties in terms of wear, temperature, and fatigue resistance. And this can all be demonstrated and can benefit industries such as nuclear manufacturing, aero engine, medical, automotive, oil and gas. The more metal additive manufacturing that we use, the bigger is this market, which is growing threefold in 5 years, as I show you. We need to develop new alloys to make 3D printing more attractive, more recyclable, to minimize its energy use. And I think you should be questioning whether or not this is your right moment to adopt this additive manufacturing technology. And with this, I would like to finish my presentation and thank you for this. Thank you very much. And I'm ready to take questions if there are any questions.
Pedro, I have a question, apart from the one you just answered for me. Thank you very much. About and it's really about where should you start? What you've talked about the if you like the parameters of 3D printing, such as volumes and the like, and you gave some fantastic examples that ranged from the one-offs and the uniques like the medical implants to probably more batch production items like the turbine blades and bearings, for example. But if a business is sort of taken on board what you've said today and wants to sort of, okay, well, what do I look at first to see what I should change in my product or to implement this new approach?
I think one way to, so this is difficult to answer because it's very much industry dependent, but the way I would say it is, what are the most critical components, metallic components in your assembly? And what is the demand in terms of properties? And if those properties that are demanded are, for instance, irradiation resistance, fatigue, high strength, wear, for example, those components that are low volume and that have complex shape would be the first ones that I would address. So that would be my first question. That will enhance the functionality of them and would allow them to improve your output. In the long run, I can redesign entire products around 3D printing, but that would be more of a long-term ambition. And that depends on the type of industry that you're in. So to answer your question specifically, I would locate those critical components that are demanding in terms of properties, and I would seriously consider replacing them. In the long run, I'll try to design entirely new products like the body armor. I mentioned the armor. You can have new body armor, for instance, with a lattice structure at the center, designing all the beams in the lattice so that bullets are stopped.
Okay, thank you. I think we have some other questions, Jenny, don't we?
We do, yes. So first question from Rob Short. Which industries will, I'm assuming that's adopt metal additive manufacturing first?
The ones that have adopted it so far are aerospace. So as I mentioned, the fuel nozzle, I read a few days ago that 30,000 of these parts have already been 3D printed. It is being used for instance, oil industry to produce elements, tubing, pipe, connectors. And also you could 3D print components for vintage classic cars, and that could be done. And I think is being done at the moment. I am aware of a number of parts that are replaced in applications, tailored applications, for example, related to energy. and there is a massive effort to produce nuclear reactor components that are 3D printed.
Great, thank you, Pedro. Got another question from Amar Bahira. What benefits, if any, do you see from hybridizing metal additive manufacturing with other processes, and which processes do you see best suited for hybridization?
Hybridization of metal additive manufacturing with other processes. Okay, so other processes is a bit general, but let me tell you what we are working on. For instance, the most obvious example would be, there are two examples that come to mind. One is to do something where you mix a forged product to a 3D printed one. And that is an idea that we are attempting, for example, with fuel cladding, where you have zirconium rods. And on top of those zirconium rods, you print a jacket that is irradiation resistant. In that way, most of the material is low cost one, but then the jacket of the material is the one that gives you the best properties. So that's one example. The other one is simply cladding or protection of worn components. For instance, I know that there are efforts to understand how you can 3D print on used rail track layers that are wear resistant. And I guess that principle could be extended to, for example, worn surfaces in large wind turbine bearings. So you can use 3D printing as a means to repair an existing material. So in that way, you can hybridize it, I think. I hope that answers the question. Yeah. I'll tackle the next question. Do you see additional challenges for architected materials for certification, for serial production? I see a lot of potential of architected materials for serial production, and I think there's great future there. I think we just start to see the potential of the architected materials, especially because, as I said, most people are only using this old-fashioned version of powder that is printed according to only one property. But when people start to realize that the architected materials can have tailored microstructures and properties in the beam, an entirely new universe appears because you can have different properties across the component. Right. So Mark didn't come back to me. Okay. Is there any other question, please?
Yeah, we've just had a question through from Catherine. What challenges do you expect to face from industry in adoption of these new manufacturing techniques, such as verification?
That's I know that there's a big effort across continents in Europe and in the US to certify 3D printed components. So there are some protocols for certification of them at the moment. So the standards actually exist. ASTM in the US, the British standard, EU regulations. So I'm pretty sure that within, the problem is that, as I said, we need to design new materials for 3D printing to conceive those new materials. And that will require its own certification, but we're in the process of doing it. We're not idle, really. Is there a sorry?
Yeah, I was just going to say we've got two questions here from Ilangawan.
Yeah.
First one, is there an NDT method developed for additively manufactured metal parts?
They're non-destructive testing, so which is the NDT meaning, the meaning of the acronym. So look, Yes, there is. Whenever we design or produce an additively manufactured component, it is usually tested adopting the usual techniques. But you're right that these usual techniques are destructive, for example, tensile test, Charpy testing, and so on. There is, computer tomography combining X-rays with imaging allows you to appraise more or less the overall quality of the product. There's the Archimedes test, which the Archimedes test measures how compact the build is, whether there's a lot of porosity within it. So that would be another one. But it's a bit difficult to talk about a more general method that deals with the specificity of it. And you're right that that's something that could be developed. And non-destructive testing to appraise metal additive manufacturing would be a great, a great contribution. Yeah.
And the second question: how good are we at this current stage in identifying the fracture mechanics of additively manufactured metal parts?
How good are we at identifying? That's a very nice question because it can be answered academically or industrially. I'll answer it industrially. Industrially, I think we're well equipped at the moment. There's a lot of information as to what is going on around the mechanics of the fracture of additively manufactured component. There are many unknowns, but I think the overall picture is there of what leads to the fracture mechanics of 3D printed components. One of my PhD students actually is working on the fracture mechanics modeling of fracture and the mechanics of the fracture of 3D printed components. And there's not much work. And definitely this is a big challenge and an area of opportunity if you're a modeler. So still the protocols that are used for continuous fracture mechanics need to be revised because our understanding of the structure of 3D printed components needs improvement. I hope that answers the question.
Okay, thanks, Pedro. We are running out of time now. So as I said, if you do have any other questions, please get in touch with us. James will be giving a little bit more information about GISMO in a minute, and I will post some more information about how you can get in touch with us in the chat.
Okay, thank you, Jenny, and thank you, Pedro. Just a minute or two at the end now to tell you a little bit more about the GISMO project and how Lancaster can help you with the sorts of issues that you heard spoken about today. Now, basically, we can help you whether you're looking at the technique for the first time, whether it's something that you already do, produce additive manufactured parts, but you're perhaps getting it done externally, would like to bring it in-house, and whether you just want to sort of prove a new concept, design, product or process, or overcome some problematic design or materials issues. We can help you across a whole range of types of issue that you may be facing. And so if from what you've heard today, you'd like to take the next step, please do get in touch with us. And there are a variety of ways that you can do that. You can get social with us and contact us and follow us on Twitter, linked up on LinkedIn, and you'll be able to look at the content, watch the content of our various seminars on YouTube. So just type in GISMO into YouTube and find us that way. Just a hint though, make sure you spell GISMO with an S or not a Z, otherwise you'll get an entirely different viewing experience. And if you'd like to get in touch with us, please do, as Jenny said, either leave your contact details in the chat here today or email us at gizmolancaster.ac.uk or give us a call on the number that you can see on the screen there. Now, in terms of follow-up from today's workshop, we're very excited to be working with our colleagues at Innovate UK Edge, who are doing a workshop on 21st of April at which Pedro will again be a guest speaker. And that's all about speeding up prototyping using design thinking and with new materials of the sort that we've mentioned today in mind. So if you'd like to find out more about that event, or if you'd like to register for it, you can either email Innovate UK Edge at the email address you see there, or again, drop your details to us and we'll pass them on to them. And in terms of the next seminar in this series from GISMO, well, the next one's coming up at the end of next month, 30th of April, when Dr. Ben Robinson will be talking about the characterization of thin films and interfaces. So that also promises to be a highly interesting topic. We'll be getting down to the nanoscale again, I suspect, to look at materials. And I'd encourage you to book up for that event as soon as you can. Get your place reserved as soon as you can. But that apart, and I can hear the church bells behind me ringing 10 o'clock already, I'd like to thank you for your participation this morning and for taking part. Hope you have the rest of a good day, and we look forward to hearing from you, speaking with you and working with you soon. Thanks a lot. Good morning.
Thank you.